Welcome to The Explainer. Today, we're pulling some fantastic insights from learn.aj.us to look right under the hood of AI. We're going to demystify the actual mechanics behind large language models, or LLMs. We all use them, we hear about them constantly, but how exactly are they generating these wild responses? Well, let's find out.
So let's jump straight into this incredibly relatable mystery. You sit down, you type a prompt into your go-to AI, and you get a great answer. But then you open a fresh chat, drop in the exact same prompt, and suddenly the wording is completely different. If computers are supposed to be these purely logical, math-driven machines, why the constant variation?
To answer that, we're going to track the life of a prompt through 5 distinct stages. We'll hit the illusion of intelligence, tokens, the next token prediction engine, temperature and sampling dials, and wrap up with the myth of perfect determinism. Okay, stage 1, the illusion of intelligence, and reprogramming our mental model of how AI actually operates. The absolutely crucial thing we have to grasp right off the bat is the fundamental difference between the software we grew up with and the AI of today. Traditional programming is rigid. It relies on explicit, hard-coded rules for logic and grammar, making it completely deterministic. But large language models, they're totally fluid. They rely on self-supervised probabilities and a next token prediction paradigm. They don't learn a single fixed rule about grammar. Instead, by churning through massive amounts of text, they just figure out which word continuations are mathematically the most plausible. It's honestly wild how fast we arrived at this paradigm shift. Back in 2015, ResNet gave us residual connections, which finally let us build much deeper networks without them breaking down. Then, boom, 2017, Google drops the famous Attention is All You Need paper, introducing the transformer architecture. Fast forward to right now, and that exact transformer architecture is the engine powering today's massive models like GPT, Meta's Llama, and Google's Gemini. The self-attention mechanism inside it just lets the model look at entire sequences of text and capture context in a way we'd never seen before. Moving on to stage 2, tokens. Think of this as the AI alphabet, or how these machines actually read human language. Before the AI can predict anything, it has to translate our text into numbers. You'd logically think it just reads whole words, right? But pure word-level tokenization is super brittle. If the AI sees a word it hasn't explicitly been trained on, it just breaks. Now, on the flip side, chopping text into individual characters handles typos beautifully, but it creates sequences that are way too long and computationally expensive. So, the industry sweet spot is subword tokenization, specifically byte pair encoding, or BPE. It slices complex words into recognizable chunks, like it might split the word unhappy into un and happy. It's basically the perfect balance. Once the text is chopped into these subword tokens, it's time for the math. To interact with the model's vocabulary, which in older models like GPT-2 is exactly 50,257 unique tokens, the system runs your prompt through 4 specific steps. It assigns an ID, fetches an embedding to turn it into a 768-dimensional vector, adds positional encoding so it actually knows the order of the words, and sums it all up. This is how human semantic meaning gets translated into raw data a neural network can crunch. Which brings us nicely to stage 3, the next token prediction engine. This is the guessing game at the absolute heart of AI. If you take absolutely nothing else away from this explainer today, remember this. The AI is not retrieving a pre-written paragraph from some hidden database. It's just playing autocomplete on steroids. It looks at the context of your prompt, mathematically ranks every single possible word in its vocabulary that could logically come next, and assigns a probability score to each and every one. And the crazy part is the looping nature of it. Step 1, the system produces raw mathematical scores called logits. Step 2, it converts those to percentages and samples a winning token. Step 3, and this is where the magic happens, it appends that newly guessed token to your original prompt and feeds the whole thing right back into itself to guess the next word. It literally builds its final output one single solitary token at a time. Now, because the model is generating thousands of possibilities for every single word, we need a way to control how it picks the winner. Welcome to stage 4, temperature and sampling dials. This is where you actually hold the power. Let's say your prompt ends with, "The sky is." The model has scored its massive vocabulary. If you set your temperature super low, like 0.1, the AI becomes incredibly confident and deterministic. It sharpens that probability distribution. The top token, let's say blue, spikes to an 85% probability. It's playing it safe. It becomes the obvious, predictable choice. But what if you crank that temperature dial up past 1? the math completely flattens out. Suddenly, blue drops down to 30%, while lower probability tokens like clear or dark become totally viable options. It introduces randomness. This math is exactly what we perceive as creativity when an AI gives us a super poetic or surprising answer. But a quick warning, turn it up too high and the model starts picking weird, obscure tokens until you just get absolute word salad. To prevent those high temperatures from pulling the output into complete nonsense, developers use strict cutoffs. The most popular one you'll see is called top P, which is also known as nucleus sampling. The easiest way to think about top T is like a velvet rope at an exclusive club. If you set top T to 90%, it dynamically gathers up only the most likely tokens until their combined probabilities hit that 90% mark. That remaining 10%, which is made up of thousands of absurdly low probability nonsensical words, is excluded entirely. They aren't even allowed in the building to be considered. Now, you might be thinking, wait, this sounds a whole lot like what temperature does. It's incredibly common to confuse these two settings, so let's clarify how they operate as a team. It's really a two-step dance. First, temperature rescales the entire mathematical playing field. It adjusts the raw scores before any final percentages are calculated, deciding just how flat or sharp the options are going to be. Then, top steps in. Top simply truncates the candidate set after the probabilities are finalized. Basically, you use temperature to set the creative mood, and you use top P to put a safety net underneath it. All right, moving into our final stage, number 5, the myth of perfect determinism. Let's talk about the hardware reality. Now, a totally logical assumption is that if we set our temperature to exactly 0, killing all the randomness, we should get the exact same answer every single time, right? Well, there's a catch. As the Institute of AI Product Management points out, achieving 100% bit-exact reproducibility is a massive myth-buster moment in the tech space. If you're building an application expecting absolute perfection on identical prompts, you are setting yourself up for disappointment. The ultimate culprit here is the physical hardware itself. AI models run on gigantic GPU clusters. Because of concurrent server batching and a quirky math concept called floating point non-associativity, the operations are processed in parallel. This means the exact order of summation changes slightly on a microscopic level every time you run it. Now, usually that doesn't matter. But if two tokens are locked in a near tie for the number 1 spot, this tiny variance can actually flip the winner. So yes, even at 0 temperature, you can occasionally get slightly varied outputs. This is why knowing this stuff matters immensely when you're actually using AI day to day. You have to match your dials to your specific task. Need code generation or strict data extraction? Drop that temperature to 0 or 0.3. Building a helpful chatbot? Stick to the 0.2 to 0.7 range. Brainstorming a creative marketing campaign? Crank it up to 0.8 or 1.2. Oh, and a quick pro tip on repetition penalties, keep them at 0 for modern models like GPT-4 or Gemini. They rarely loop anymore, and penalizing them just degrades the quality of the output. Ultimately, the big mindset shift here is that we have to fundamentally embrace the probabilistic nature of large language models. Stop chasing perfect determinism, because the math and the physical hardware literally won't allow it. Instead, track the variance, learn how to steer the probabilities with your settings, and just set realistic expectations around stabilities. AI isn't magic. It's a beautifully complex mathematical guessing game playing out one single token at a time. So, the next time you sit down to interact with an LLM, remember that you hold the dials to this incredible engine. The only question left is, how are you going to steer it? Thanks for joining me on this explainer, and we'll catch you next time.